In this video, we're going to implement two searching algorithms in Java. So before we implement any of the methods themselves, I've added some code in this searching class that's going to help me keep track of how many times we do a comparison with each of the sorting algorithms. So you'll see I have a counter that I set to 0, and then I have a method to get the counter, update the counter, and then reset the counter. So the first method we're going to implement is going to be a linear search. Now, linear search is probably familiar to you, even if you haven't called it by that name before. What we're going to do is we're going to search through an array, starting at the beginning, and then we'll search each index consecutively until we find the target. So here our target is 6. We start looking at index 0, which has 8. That's not 6. 4 is next. That's not 6. 1. And then in index 3, we see a 6, and so now we're done. Now, if the element we're looking for, the target element, is not in the array, we'll actually have to scan through the entire array before we can make that determination. So let's see how we would implement linear search in Java. We want to be able to search anything, so we're going to have a generic array, but we want to say that whatever that generic type is, we want to make sure that it extends the comparable interface so that we can use compare to. And our function is going to be called linear search. It's going to take an array of elements of that generic type. We're going to pass the min and max array indices that we want to search between. And then we're going to pass a target element. So the first thing we want to do is set up a generic object to hold our return value. And that'll start off as being null because at first we don't even know if that target exists. And keep in mind, it may seem weird. Well, if I'm searching for this, why don't I just return a Boolean, yes, it's found or not? And the reason is that you only need to have enough of this object filled in to be able to compare it. And we'll see that in an example later. And that is comparable. There we go. And I'm going to return, instead of the target, I'm going to return a reference to the element that's in the data because that object may be more fully formed. In the case of an integer or a character or a string, maybe it's not a big distinction, but certainly if we're talking about a user-defined class that has multiple fields, we may not have all the fields information filled in. So for example, we'll do a student record, and with a student record, if they have your student number or your name, they can find your transcript and other information about you. So I'm going to have an integer index, and I'm going to call it current, and that's going to be set to the minimum index that I want to search in the array. I also need to reset the counter so that I can get some statistics about how many elements I have to compare. So now let's get to the meat of the searching algorithm. So while current is less than or equal to max, and I also am going to stop searching once I find the target, but I'll actually break out of this loop if that happens. So I'm going to increment the counter because I'm about to do a comparison. And if the data stored in the current index, when I compare it to the target, if they're the same, so compare to will return 0 in that case, I'm going to set my return to the element in the current index. And now I'm done, so I'll break out of the loop. Again, I could do another comparison up here to check to see, hey, if it set a done flag or is current not equal to null, but I think breaking out of the loop is a little cleaner. Now, if I haven't found it, I need to set current, or I need to increment current. If I haven't found it, I'll get to this line of code and I'll increment current. So don't lose track of the difference between counter and current. They do have similar spelling, but counter is what I'm using to keep track of the comparisons. It's not actually part of the search. Now, once I've exited this loop, I can return the object. And it looks like I already did that. So here, if I didn't find it, return will be null. But if I did find it, I'll break out of this loop and I'll return data current. Now, one other thing here that I want to change is normally somebody's not going to say, hey, find this element within these two indices, or between these two indices of the array. So I'm going to overload this method where you can pass just the array and a target. And it's going to return linear search on data between 0 and the length of the data -1, because that's the highest index that we'll ever search. And we're still looking for target. And that is our linear search algorithm. Now, one thing that's nice about linear search is that it'll always work. I don't have to have any special arrangement in the array. However, if the array happens to be sorted, we can improve on this. So in a binary search, we don't start at the beginning, we start in the middle. And you may say, hey, the binary search is magical. It found it in just one try. Well, that just is the way this particular array is set up. If we're looking for 6, the middle is right here, so we're going to round down to index 3, and index 3 happens to have the target. Well, what if it doesn't have the target? So if we want to find 12, we're going to start here. But notice this array is sorted, so I can assume, actually, no. Since the array is sorted, I know that 12 is not going to appear to the left of 6 because the array is sorted. So anything larger than 6 has to appear on the left side of the array. So guess what? I never have to look at these 3 elements. So now I'm going to find the middle element of this part of the array, which is here. So again, I round down, so it's going to be 5. Index 5 holds the element 9. 9 is smaller than 12. So again, I know what I'm looking for is to the left. And so I have these two to search, and the middle element of these two would be the lower one, which is index 6. Index 6 holds 12, so I found my target. Let's suppose I want to find 4. Again, I start in the middle, which is index 3, which holds 6. 4 is less than 6, so I know that it has to appear on the right side of the array. I can now disregard all of these elements. So the middle element of this subarray is 2. Actually, it's these 4 because I know it's not here and I know it's not to the left. So it's 2. 4 is greater than 2, so I'm going to search to the right, and there it is. So you can see that binary search is a lot more efficient because there's no circumstance in which I have to look at every single element of the array. And the notes have some information on the analysis here, but it turns out linear search is a linear algorithm, it's order n. But binary search, since we cut the search pool in half each time, it's actually going to be a log n algorithm, which is much more efficient. So how do we implement our binary search? Well, the first thing is I'm going to go ahead and snag these first 6 lines of my linear search, and I'm going to change it to binary search because I'm going to do the exact same thing I did above, where you can either give me 2 indices or you can give me just the array and the target you're looking for. So just as we did above, we start off, we're going to assume that we don't find it, and we're actually going to write this recursively. And having the min and max here is going to make things easier that way. So the base case is going to be if min is greater than max, I'm going to return null. And that would happen if there's only one element in my remaining search pool. If that fails, then I'm going to go either to the left or right. And once I do that, min and max will swap, and the min will actually be larger than the max, or the max will be smaller than the min, depending on which way I move at that last step. And if that doesn't make sense, it will be more clear later. So since this is recursive, I'm actually going to need to do my reset counter here. Because if I reset it in my recursive call, I'm going to keep resetting it every time I recurse, and that's not going to give me the right answer. And I'm going to return ret as my return value. I need to find that midpoint. Remember, that's where we start in a binary search. So the midpoint is going to be the min plus max minus min divided by 2. Now you may think, why don't I do min plus max divided by 2? Well, if I have a very big number here, I could conceivably get an integer overflow if I say min plus max divided by 2. So this gives me the same result. So I'm about to do a comparison. So I'm going to increment the counter. And I don't want to have to keep doing compare to, so I'm going to do it just once. So my comparison result is going to be the midpoint compared to the target. And then if the comparison is equal to 0, then I found what I'm looking for, and it should be comparison result. In this case, if the comparison is 0, I'm going to return data mid, because that's what I'm looking for. And the reason I did this compare to again was because I've got to check it, not just if it's equal, but I need to determine if it's less than or greater than 0 if it's not equal. So if that comparison result is greater than 0, so what this would mean is that the target is less than the midpoint, or the midpoint is greater than the target, however you want to think about that. So if that's the case, I'm going to return a binary search. I'm going to pass the data. I'm going to start in the same place, but now I know it's to the left of the midpoint, so I'll say mid minus 1, and then I'll search for the target. Otherwise, it's not equal to, it's not less than, so it must be greater than. That being the case, I'm going to return a binary search starting at mid plus 1, because I'm going to search to the right of the midpoint, because in this case, the target is greater than the element stored at the midpoint. And that concludes my binary search method, except that I did start and end, not min and max. Okay, so let's see how we are going to use this method. And before we do that, I have created a simple student record class that has a student name, their number, and their GPA. They get assigned a student number that starts at 1024, and you can see I'm using a static int to do that here, and they have a name and a GPA. So I have getters and setters, I have a toString, and then the compare to returns a comparison with their name. So I don't actually need a GPA and a student number to find a student record. All I need is their name, and we'll see how I make use of that. I've also overridden equals and hash value, but for now you don't need to worry about that. So in my driver class, I'm going to create an integer array of 5,000 elements. And I'm going to fill that like so. I'm going to do some searching for student records. So let me create a student record array. And we'll do a student array of 10 records. And so here they all are. So let's print out those student records so that we can see them all. Okay, so we have the student records and we have an array of integers, so let's do some searches. So my result of my search is going to be a linear search over array A, and I'll start looking for 4. And actually, to simplify this, I'm going to create an array of integers. And this way I can just cycle through this array. I don't have to keep typing stuff. So for every target in targets, I'm going to search for the target. And then I'm going to say that I'm printing the target. And then I'm going to say how many times it took to find that result. Actually, I should print the result here, I think. No, I print the target first. Then I'm going to print the result. Then I'll print the counter. And a closing parenthesis. And I think that all looks good. So let's test this to see if it works. And it's not going to work until I close that loop. And this is telling me I have a bug. What's the bug here? Did I misspell linear search? And that's public. Nope, it's there. So when I run this, you can see here's all my students. We'll worry about those later. And then you can see that the further I have to go into the array, remember that array is sorted because I'm just multiplying the index by 2 when I initialize it. You can see the further I go into the array, the more comparisons I have to do. And it takes me 5,000 comparisons to find that a number does not exist in the array. So 41 doesn't exist, 10,000 doesn't exist, and both times I have to search through the entire array to determine that. So let's copy this and do it for binary search. So same loop we did before, but now we're going to do binary search. Actually, instead of this new line, I'll just call print line twice. That way I'm not polluting up my strings here. So when I run, notice with binary search, I get some really unfortunate results. That is not good. So let me debug this. I'm hoping I'm calling binary search calls linear search. I didn't change that, copy and paste error. Okay, so good. I'm not going to have to debug much. Now when I run, you can see I get much better results with binary search. So look at these numbers and then compare them to binary search. Now, whether I find it or don't find it, it doesn't make a lot of difference. It looks like it's going to be between 11 and 13 comparisons that I have to do. But compare that on average to here. The only time linear search beats binary search is when I'm searching for a small number that I know is at the beginning of the array. Now the downside of binary search, if this array wasn't sorted, this wouldn't work because I'm only looking at very few of the actual elements in the array. One last example, just to show how it works to search for a student record. So this is going to be the result. I'm going to do a binary search through the students, and my target is going to be a new student record. And I'm going to search for Floyd Harrington. And I'll print out the result. It's not liking S here. S can't be resolved to a variable. Oh, I put this in the wrong spot. It does not belong in my searching class. And I apologize for that mistake. It belongs in my driver. But I do want to return something from binary search. So let's do that. Okay, so I fixed that. This is in my driver now. And when I run, notice now, even though I only knew Floyd's name, now I get the student number and his GPA. So this is how to implement linear and binary search in Java.